give a few hints to some of the assignments. The first problem that I want to discuss is about the two-dimensional isotropic harmonic oscillator and how to see degeneracy. What we have to do is that we know what the harmonic oscillator is, what the solutions are in the Cartesian coordinates. So n is the principal quantum number. I made an error. It should be principal, not princip. It should be PAL, not PLE. Is the principal quantum number. And so we can think of n in terms of nx and ny. So if I do that, then here is n of x and n of y. So if n is 0, well, it can only happen in one way. Nx can be 0, and y can be 0. Then my wave function psi of n is going to be just simply given by h0 of x, h0 of y, e to the power minus, let me just make a bit of room here, x squared plus y squared divided by 2. So what I would like you to do is to express this in terms of the eigenfunctions of Lz. So Lz means that we want to express in polar coordinates. So for Lz operator is given something like this. So x and y are related to r and phi through these formulae. So I can then translate this, and this for n0 for these cases, they're just constants, right? So up to normalization, this is just going to be some constant time e to the power minus r squared by 2, right? So this is the first one, and then one can say, okay, what about the next one? So if n is 1, then right. So when n is 1, nx and ny can be 1 in, it can be either this can be 1 and this can be 0, this can be 0 and this can be 1. So in that case, we have a twofold degeneracy. And in that case, we have x0 of x, h0 of x, h1 of y, and here we have minus the same square, ax plus y squared by 2. And in this case, we have, this should be 1 and this should be 0. 1, 0, and this should be 0, h0 of x, and h1 of y, and e minus x squared plus y squared by 2. And we know that up to normalization, h1, we know what h1 of x is, it's just x. So we are going to have the wave function here, x e minus r squared by 2. But x is actually given in terms, we have to express it in terms of r. So here we'll have, let me rewrite this, we'll have r cosine of theta e to the power minus r squared by 2. But cosine of theta can be written as e to the power, so cosine of phi, e to the power phi plus e to the minus phi by 2. Let me just write that 2 here. So here we see that this is an function of Lz with eigenvalue +1, and this is an eigenfunction of Lz with eigenfunction eigenvalue -1. So we can create a new column in our table. So we create a new column in our table where we write down what the m eigenvalues are. And the n eigenvalue of this thing is 0. And here we have two eigenvalues, +1 and -1, a particular linear combination of that. And what we see here is similarly, we'll have r, but here we will get y. So y is sine. So we'll get a different linear combination. Here e to the power I phi, and there'll be 1/2i minus e to the power minus I phi, e to the power minus r squared by 2. Right? So here we'll have, but you see here we get a different eigenfunction. We get a different linear combination here than here, right? But the idea is that when we express it in the polar coordinates, we get the eigenvalues of m to be +1 and -1. So similarly, if you do n equals to 2, you can then satisfy this in three different ways. Well, you can have 1 and 1, or you can have 2 and 0, and you can have 0 and 2. And you can write the Cartesian coordinate wave functions here. And if you then go over here and express it in terms of phi and r, what you will see is that you will see that there are three linearly independent wave functions, and they're made out of linear combinations of wave functions which have m eigenvalue m +2, m -2, and 0, right? So these are the two different ways of looking at it. While these are essentially way of looking at them, looking at the oscillations in the x and y direction, these you can think of it as oscillating clockwise and counterclockwise with different frequency or velocities. Okay, so this is the solution to 5e. And I want you to explain it in your words. I want you to do this table in your own way. Okay, so next you asked for explanation of the last problem in the problem set number 2. And the last problem is really about Euler angles, right? So what are Euler angles? This is just a way that to represent three-dimensional rotations in terms of three consecutive rotations which are not around the same axis. And this was basically the way that Euler originally understood or analyzed rotation. So I think the first one is obvious. The first two problems is in terms of passive and active and passive rotation. So if you do over here, we are just changing the coordinate system, and we are changing the coordinate system in a counterclockwise fashion. And so this rotation, this vector r is not changing, but its components are. And what's happening is that these are the changes in the x and y coordinate axes, right? So from there you can figure out, how the different components of r are changing. The other one is actually rotating this vector in doing an active transformation in which we are rotating it clockwise, and it's given by the same equation as this. So these two equations are the same, but their interpretation are different. Okay. And this is the Euler angles in which you first rotate in a counterclockwise way around the z-axis, and then you do another counterclockwise rotation around this new x prime axis, and then you do another counterclockwise rotation around this new z prime axis. And so there are three different rotations. The first one is D, the second one is C, and the third one is B. And you know what these individual rotation matrices are, and they're just given by versions of this rotation matrix, and you just multiply them together. And the big rotation matrix R you have is will look complicated, but it's also a matrix which satisfies these two conditions. R is equals to, so there should be an inverse here. So there's a typo here. This should be R inverse, and its determinant should be 1. Okay. So, and then one has the BCH formula, which is probably what you guys want help with. As for the BCH formula, I think there's also a typo here. I wrote A and B here, whereas there should be X and Y. Now, there's actually no very easy way to derive this, the first few terms of this. And this is not something that I kind of will be examining you, but if one wants, there are several brute force ways of defining this. But there is really no, as far as I know, there is no closed form way of deriving this. And as for this one, this is actually not very hard. If you think of the matrix X as some Hermitian matrix or some matrix that can be diagonalizable, then it just follows that you can diagonalize this e to the power x matrix by doing a unitary transformation. And because unitary transformations of unitary transformations, the determinants are going to cancel out from each other. And this is, so the same unitary transformation is, of course, going to be the unitary transformation that diagonalizes x. And of course, because of the trace, there is not going to be, there is a, this thing is also going to be diagonal. Right? Once you've diagonalized, say, the left-hand matrix, it's kind of easy to see that the determinant of this is just the product of e to the power, the eigenvalues of x. And because they're exponential, it becomes e to the power the sum of the eigenvalues, which is exactly what the right-hand side is. So I think that should cover everything.